Welcome back, everybody. This is example 7.6, the slide-loving pig, and this may be a little bit different variant than you're used to seeing, but I thought it might be a little more helpful for you. So let's take a look at the slide-loving pig and see if you can follow along. Reading the question, it says the slide-loving pig slides down a certain 27-degree incline in twice the time it would take to slide down the same slide if it were frictionless. All right, so we want to find out the coefficient of kinetic friction for the slide that has friction. All right, so let's a little bit of background right here. First of all, I am going to anything that deals with the side that has friction, I'm going to notate with an F, with a subscript F. All right, lowercase f. Without friction, I'm going to do it with a subscript 0 for none. All right, we see that both slides are 27 degrees inclined from the horizontal. It's essentially the same pig, but the one slide has friction. And as the pigs slide down, we see that it takes the one pig with friction twice as long as the pig without. Or if it's the same pig, it would take him twice as long as if you were to go down the frictionless one. So we can make a statement about our time. The time with friction is 2 times the time without friction. All right, so we can write that down. There's a few other assumptions we can make as well. It's not explicitly stated, but it says it's the same slide, and so that means the displacement down the face of the slide is going to be the same in both cases. Delta x with friction is the same thing as delta x without friction. Another assumption we can make that may not be as obvious is, as the animation indicated, the initial velocity of the pig was 0. It started from rest and then accelerated down the slide at different rates, of course. Okay? So with these assumptions in mind, let's go ahead and make some statements about net force on each pig in each scenario. All right? First of all, it's always true that the net force on the pig, whether on the friction slide or the non-friction side, is going to be mass times acceleration. All right? Notice the subscripts F and 0. All right? That's Newton's second law. But it's also true that the net force on the pig in each circumstance is a function of a series of component forces that are adding up to give him that net force. And so what are those forces that are acting on the pig in each circumstance? Well, of course, the pig has mass, and being on Earth is subject to gravity, and so the weight force is going to be directed straight down. But the weight force isn't completely directed down the face of the slide. No, that's going to be the parallel force, right? The force parallel. I have it labeled on the left-hand side with the F and with the 0 on the right-hand side too. Although, really, since it's the same pig, they should be the same thing. There's also the force perpendicular, directed, the weight part of the pig directed into the face of the slide right there. And so that's our force perpendicular. Well, if there's going to be a force perpendicular, there's also got to be some sort of a normal force, right? Or a supporting force acting straight upwards, keeping the pig from collapsing the slide. So normal force is going to be directed straight up, but in the opposite direction as the force perpendicular. And so far, both of these scenarios look the same, but there is one difference, and that is the one on the left has kinetic friction acting against it, which is what causes it to slide down the slide slower. Okay? So let's look at the component forces that are acting on each pig in the direction, and you might say in the parallel direction of each slide. And we can say that on the left-hand side, it's force parallel minus coefficient of kinetic friction, or I'm sorry, minus the friction force. And on the right-hand side, the only net force that's acting on the pig is the force parallel. So these are going to be our statements that set us off to solving for this problem right here. Now keep in mind, in yellow, that's the kinetic friction force. In there is going to be our coefficient of kinetic friction, which we're solving for, but it's just not out yet. Okay, so let's get rid of everything else, and of course each of these two statements about net force we can set equal to each other, so we're going to do just that. All right, mass times acceleration equals the sum of all the forces in each case, for the friction slide as well as the non-friction slide. Well, what is our link between the two slides, or the pig on the two slides? Well, time is our link, right? We know time is twice as much on the one side as it is on the other. So let's ask ourselves, look at what we have right here. Where is time likely to come from, or which of these values is likely to have time in it? Mass, acceleration, force? Well, you know from kinematics it's going to be acceleration, right? Acceleration is a function of time. So let's set these equal to acceleration. Let's just rearrange them like so. Okay? So we have these statements now about acceleration that are set equal to the forces involved on each pig divided by the mass of the pig, which, by the way, we don't know, but that's okay. So let's think back to kinematics for a second and make some space for ourselves right here and ask ourselves, what equation deals with acceleration and time? And oh, by the way, we have some knowledge of displacement and some knowledge of the initial velocity on each pig. Well, I think this one right here will probably do as well. Right? This is kind of our utility equation from kinematics. And so we have some sort of link between time and acceleration that we can possibly link to these statements about net force and mass and acceleration. All right? Now, it appeared that we just made this a lot more complex, which we did at first, but this is going to become easier real quick. First of all, what part of these kinematics equations can we get rid of right away? And you're going to say initial velocity, right? Because initial velocity being 0 means that that whole thing drops right out. All right? Well, since we have statements for acceleration above, why don't we take these kinematics equations and turn them into statements for acceleration below by just rearranging them to solve for acceleration? All right? What have we done right here? Well, we've set up a means by which we can substitute. We've got acceleration, statement for acceleration above and below. Let's just set them equal to each other. And acceleration is equal to both of those on either side of it. So in this case, acceleration just drops out entirely. So now we have statements about displacement and time being equal to force and mass on the other side. Okay? Well, where do we go from here? Well, we still have that link between the friction slide and the non-friction slide as being time, right? So let's rearrange these once again, and maybe we can substitute and have time drop out. So let's state these with respect to time. All right, we rewrote our equations and set them equal to time. By the way, I'm going to move the time on the right over to the left, just like that. Okay. So now it's a little bit more obvious about how we can link these two equations together. Remember, these two equations are from two different slides, but we can link them together. We will be able to in just a second. Now think back. What's the difference in the times? Well, the time with the side with friction is twice as long as the side without friction, right? Now look up above. We've got time with friction squared and time without friction squared. So what we'll need to do is we'll say, okay, well, let's make a statement about these times squared. So time with friction squared is going to equal 2 times the time without friction, parentheses, squared. See what happened? All right, if that, well, the statement that's grayed out right now, if that is true, then we should be able to square both of those, but we're going to have to square that 2 as well, right? The 2 that's out in front of the time without friction. Well, if we square that and put it out in front, it's going to become a 4. So we can say that our time with friction squared equals 4 times the time with friction squared equals 4 times the time without friction squared. You still with me? All right. Well, let's look up above and say, okay, we can drop our times out now because we have a statement for time with friction squared and time without friction squared. Let's just drop them right in just like that. The only difference is that there's a 4 in front of the one on the right because of that relationship between the times. Okay, this right here is going to be our working equation from here on out to solve to the end. No more substitutions. Everything's there. We just need to solve for that mu k, that coefficient of kinetic friction that is somehow locked up in that, that yellow kinetic friction force. Excuse me. Okay? So let's get this all by itself. Take a look at it. Well, what's the first thing you see? Well, I see some fractions. I don't like fractions. Let's put everything into one straight line, straight across. So we're going to multiply our denominators up, and then come up there like that. Okay? Now, I've had this green force parallel on both sides there for quite a while now, but I think you know that the force parallel can be written in a little more detail. What is the force parallel of anything moving down the ramp? Well, it's mg times the sine of theta, the sine of that angle right there. So let's go ahead and plug them in. Mg sine theta and mg sine theta, they plug in there for the force parallel. All right. It seems like we're getting more complex, and we are, at least initially, but this is still the same equation. All right. What about the kinetic friction force in yellow right there? Can we write that in any more detail? And I think you know also that the answer to that is yes too, right? What's our definition for the kinetic friction force? Well, it's the normal force times, and this is the big thing, the coefficient of kinetic friction, that mu k right there. So let's just take that and plug it right in. And now all of a sudden, mu k, our coefficient of kinetic friction, is in our equation. And the light is at the end of the tunnel. We can see the end right here. We just need to rearrange some things and solve for it. All right. Well, one little speed bump before doing that is now we've got this n in front of us, right? This normal force, n. What is that going to be equal to? What do we plug in there? Well, in most cases, objects sliding down the slide, the normal force is going to be the force perpendicular, right? It's the supporting force that supports the weight of the object, in this case the pig, being directed perpendicularly into the face of the slide. So we can say force perpendicular goes right in there. And you also know that the force perpendicular can also be written in more detail. Force parallel is mg sine theta, right? Force perpendicular is going to be mg cosine theta. And there we go. All right. Our equation seems to be getting longer and longer, not shorter and shorter, but that's okay. Because now kind of the fun part happens where we're going to start getting rid of stuff left and right. I mean, after all, we know what g is, right? But we don't know the mass of the pig. We don't know the displacement down the ramp, all right? And we certainly don't know the coefficient of kinetic friction. That's what we're solving for. But let's start getting rid of things now. Look at that 2 times m times delta x on both sides. Multiplied by both sides, right? Let's just get rid of that right now. Boom, that goes away. They just cancel right out. And now look, everything that's in our brackets on both sides, everything is basically multiplied by mg, right? We could really factor that out. Let's factor out the mg on the left-hand side and factor out the mg on the right-hand side. So that comes out front right there. What can we do with that? Well, that too can get canceled out because it's the same on both sides. So that goes away, and our equation is now getting smaller and smaller. That's good news. Now, a little bit of a problem right here is the fact that our mu k, our coefficient of kinetic friction, is locked inside that parentheses right there, and we don't like that in there. We want to be able to break that open and isolate it by itself. So what can we do? We can distribute our 4 to the sine theta and to the mu k cosine theta. So let's do just that. All right. What do we do next? Well, we've got that mu k times 4 cosine theta, and that's okay where it is, but I don't really like the minus sign in front of it. So I'm going to add that whole expression to both sides, so it comes over to the left. And that sine of theta all by itself over on the left, I'm going to subtract that and bring that over to the right. Okay. Now, look at the right-hand side. 4 sine theta minus sine theta. This is about as easy of a question as you're going to get. 4 of anything minus anything. It's going to be 3 of anything, right? 3 sine theta. So that simplifies. All right, what do we do to get mu k, the coefficient of kinetic friction, all by itself? We're going to divide by 4 cosine theta, so that comes down below. And even this right here can be simplified a little bit. That's kind of like saying 3/4 times sine of theta over cosine theta. So let's take that 3/4 out and turn it into a decimal point. To me, that's 0.75. We're almost there. You could probably solve it like this, but it can even get simpler. What's the sine of theta over cosine theta? Okay, sine of anything over cosine of anything. That's tangent, right? Tangent of anything. And we know what that anything is. That's one of the few givens we were given. That theta is 27 degrees. So, from all that mess, all that substituting and rearranging and distributing and factoring, we now have a working equation to solve for our coefficient of kinetic friction. What do you get if you key in 0.75 times tangent of 27 degrees? 0.38. That's your answer. Box it up, because that's the end. Thanks for watching. I'll see you on the next one.